Thank you very much for that nice introduction, and thanks for inviting me here today. And it's been a great meeting so far, and previous speakers yesterday and this morning already said FAIR is unbelievably important, and interoperability, you can get this quote from almost anybody that you've got to have integrated databases, and to do that you need something like ontologies. And ontologies for me are the only silver bullet that I'm really aware of for really doing interoperability and FAIR overall. And since we've been using the word ontology so much, I think everybody understands it. But when I use the word ontology, I will include everything from controlled vocabularies up through very fancy, very articulate descriptions of what terms mean. So I'm going to talk a little bit briefly about our ontology development process. And I've got 2 stars here because there's 2 pictures that I'm going to leave you with at the end, which is 1 for developing ontologies, and then 2 using ontologies to enable smart integrated systems. And we've heard some really nice examples today. So there's a lot of places that you can get as starting points: your use cases, existing vocabularies, templates, data dictionaries and code books, expert interviews. And I'm going to give a bunch of examples exemplified by CHEAR, the Child Health Exposure Analysis Repository. And I'm part of the data center. I lead the data science core, which that call actually basically defined data science as interoperability and vocabularies. And CHEAR basically is a program that says, if you've got a child health analysis or a project, please add some exposure to it. And so we basically need to cover exposure and health for children, but really for all of human health. And actually the follow-on program for CHEAR will be here, which is not limiting it to just children. So there's typically a lot of foundational vocabularies and ontologies, and then our stuff is kind of in the middle. So we generate the ontology, but when we make ontologies, we probably create less than 20% of the terms. Our main work is identifying what our starting point should be and how to do mappings. And then we don't just create an ontology and not use it. So we use it within the human-aware data acquisition framework, and we use it in some other frameworks as well. And then behind the scenes, there's knowledge graphs that kind of power everything. And there's repositories, such as some of the nice examples that we saw. Not that we're connected with links today, but we should be, and we should talk. And then ultimately have some knowledge enhanced search. So I think many people know something about CHEAR. So we want to encode the terminology. And actually, we did this in kind of a use case oriented way. So what do we know child health exposure analysis needs to do? So don't do an ontology for the world because we wouldn't have enough time and money to do it. Do it by what we know is coming in. And then make sure that we're findable, accessible, interoperable, and reusable, and replicable. Yeah, the FAIR should have 2 R's. And ontologies encode the relationships, basically supporting the INR in FAIR, and the ontology-enabled infrastructure helps you find it and access it, basically supporting the FNA in FAIR. And actually, both of them kind of support the replicability. So our foundation, basically we pull in what we're going to use very heavily. So we import, if you're familiar with ontology terms, so like pull in the entire ontology. Our foundation is the semantic science integrated ontology, which by itself has integrated a whole lot of ontologies. Pravo, the World Wide Web Consortium's recommendation for provenance on the web, the units ontology, then we have the human-aware science ontology that integrates a lot of other ontologies. And the reason it's human-aware is because humans come in and calibrate things and create studies. So it's debatable whether that's the perfect naming, but anyway, that's what it is. And VSTO was an early ontology for virtual observatories. We use the instrument foundational piece and then extend it, and the environment ontology. And these are the things that we import. And then this is a really important notion. The minimum information to reference an external ontology term, or myriad. So wonderful giant ontologies like CHEAR, really useful, but they're really big. So we just reference those terms. So we reference CHEAR, Stato, PubChem, Uberon, the disease ontology, Uniprot, Cogat, EXO, and this is growing because basically we put stuff in as we need it. And then we use annotations from SCOS, the Simple Knowledge Organization System, and Dublin Core. So what do we have to do? We have to get all that content. So we have to get the schemas, and conveniently, this program requires you to have a data dictionary and a code book if you're going to submit to it. So we get these data dictionary and code books, but you know, when we're lucky, we get things like column headers like this that you can actually guess what they mean, but sometimes the column headers are like T2. So we got to map them to things that we know about. So we got to map them to like humans that are playing the role of a child in relationship to a mother, and they have important things like gestational age and time, super important. And if you want to learn about our semantic data dictionary approach, this is one good paper for it. So basically, semantic data dictionaries allow you to take a data dictionary and then connect it semantically. So thus, in a structured form related to terminology that we know. And then with that, you can do an auto ingest of data that's compliant with your data dictionary and your code book. And there's a whole testing infrastructure behind the scenes too that says, is your semantic data dictionary actually consistent, and does it use terms? Does it create a new term? Oh, and this is a place where if you can't map a term, you say, hey, I got a new term. Maybe I should map it like Cogat was we recently got a study that was measuring a bunch of cognitive measures. So we added Cogat more recently, which is an ontology that has a lot of cognitive measures. So our epidemiologists actually fill this out. Over time, it will be the PI. Well, the hope is that it'll be the PI, but today it's the epidemiologists at the data center that fill this out. And then we've got to integrate stuff like here are 2 levels of education that we got into studies. You know, one's very coarse, one's much more granular. And ultimately, we want to be able to support our biostatisticians to do pooled studies where they actually understand what those terms mean together. So the ontology is supporting the mapping and integration. It helps figure out when you've got proxies for things. So sometimes you want something like a Fenton weighted z-score, but you can calculate that from birth weight, gestational age, gender, and then this chart. So it's not always that you have to have the exact thing that you're looking at if you can actually determine it. And the ontology does simple things like we've got a bunch of studies. Some of them had APGAR scores above 10, which you shouldn't have. So it helps you do those kind of consistency checks as well. Then we've got this human-aware data acquisition framework that does a ton of stuff. It's our backend for the CHEAR portal that is actually kind of hidden behind the scenes for the geeks like my team that let you do things like search for studies or search for data, that lets a statistician ask questions like, I want some content about my children, I want birth weight, gender, gestational age at birth, I want some content about my mothers, and then I want exposures, and they've got some set here. But it also lets, I'm showing the admin view on this, it also lets, yeah, you can barely read that, the appropriate kind of people upload content, download content, search for content, add new people to your group so that you can see it during submission, during your embargo period, other people can see it later. So there's a lot of access control as well. And then you can get things, this is intentionally super small because the only data that I can show is the little bit of NHANES data that I pulled in for testing. This is actual data, which is why it's unreadable. But you can look over the metadata for the studies and then find that like your study 1 had information about blood biomarkers or children's health. And similarly, you can see distributions if you were looking over particular studies or particular instruments, like I just want the epi data or just the lab data or just the cadmium data or something. And I want particular time points, like I want studies that have first and third trimester data, or paired studies, or mothers with multiple kids. And so I can basically do kind of a precision search. And then from that precision search, I can do a download into your favorite spreadsheet so that your biostatisticians can do their lovely work. So this is the tool itself. Hot Attack has been used behind a lot of different systems, all of which have data that I can't show. One for the Gates Foundation that did healthy birth, growth, and development knowledge integration, one for some large aquatic ecosystems, one for some air quality monitoring. And actually, one of the beauties of this is my team, the computer scientists, are not doing the semantic data dictionaries. The domain people are doing the semantic data dictionaries, and the biostatisticians or the applied math or machine learning people are actually doing the requirements for what they want to see queryable. Then I wanted to also say a little bit about the ontology-enabled infrastructures that are a larger thing. So I love ontologies. I am probably one of few card-carrying ontologists in the room. I could build ontologies for the rest of my life and be a happy person. But my funders are not going to make me, are not going to pay for me to build ontologies without seeing the value. And so the ontologies are an important piece. In all my pictures, they're always the middle. And the knowledge graph that is annotated with the terms from the ontologies, but really they're part of this larger integrated framework. And we've got these efforts that one time was called SEMNEX for Semantic Numeric Exploration Tool, and another time was called Semantilytics for Semantically Aware Analytics, that make smart systems that normal humans can interact with, like by asking questions. They're all powered by the knowledge graph. They all get content in, whether it's by humans putting it in, by natural language processing, by semantic extract, transform, and load processes enabled by semantic data dictionaries, by humans doing the mapping. They all get that content in, keeping track of where you got that information, because provenance is unbelievably important. And then leveraging whatever kind of inferential support you've got, whether you're doing statistical reasoning, deductive reasoning. We heard some nice examples of some machine learning reasoning. And so then stuff gets updated into the knowledge graph, whether it was from a sound and complete reasoning system or some statistical method with that annotation, knowing that it depended on this literature that maybe came from PubMed or maybe came from some gray literature. So you want to keep track of that. And we've done this in a couple of systems. This was before our, so this work is largely funded by the IBM AI Horizons framework. But prior to that, we did some drug repurposing, and actually we've heard a couple of examples about drug repurposing, but we did it in a project that we called Redrugs, repurposing drugs with semantics. So we pulled in declarative representations of information about drugs, diseases, and proteins. And then the relationships, like whether they inhibit or enhance. I think there's 16 different relationships that we get through. There's 18 different data sources that come into this. Initially integrated by IREF, later integrated by BioTAR-DF. And then we kept track of course, where the information came from. Each interaction has evidence-driven probability. And then we calculate probability through standard Bayesian methods, but you can have your own pluggable method. Like if you like something more than, you like this resource better, you like this, this experimental method better. And then we looked at the best hypotheses. And actually, the unbelievably cool thing from my perspective for this was we looked at melanoma drugs because one of our collaborators worked at the Yale Skin Spore Lab before coming to be my PhD student. And we looked at potential melanoma drugs. We got 24 hits, 21 without looking at clinical trials, 21 of which were in clinical trials. So it was kind of great validation that the precision for suggestions based on something inhibiting some particular pathway or accelerating some particular pathway. So one of the reasons that I wanted to put this in was we had this great discussion yesterday about I love machine learning. I love statistical methods, but I don't want to say, believe me, I did nice math. And I don't really even want to say, believe me, a lot of other people believe me, and I had big data sets. I actually want to say more than that. I want to be able to say, you know, X inhibits Y, so that you can actually understand why it might be plausible that this is the case. And then further, I want to know what studies you're dependent on. And I want to know what that population distribution looks like to see whether I, as a patient, or my new patient, matches that population or not. So we've got this knowledge graph technology. In our current version, we're building this biology knowledge graph. The things that have red underneath them are future work or currently started but planned to completed work that you can query using the background knowledge base. And we've done some of that through text mining, some of it through hand curation. And you can go in through a lot of different formats. And the information is fairly rigorously modeled, although not quite at the granularity of the previous talk. So we should chat. And then that can enable things. We've explored this within breast cancer settings. We're currently doing it within diabetes, and hypertension's next. So we've got a tiny little portion of this. We're looking at breast cancer. We're looking at, we saw some HER2 examples yesterday, ERBB2, so you can see that this impacts breast cancer positively. You can see some of the drugs that relate to this particular protein. And then everything is captured, is annotated with provenance using Bravo. And everything has a nano publication, so the smallest amount of information behind the assertion. So you know where you got that lapatinib impacts ERBB2, and you know where you got the fact that ERBB2 drives breast cancer. And so you can trace back who made the claim, what other knowledge they added if you want to. Do we trust this person or this resource? And then you can do your reasoning on top of it. So, and it uses provenance-driven probabilities. One of the things that we did earlier was we looked at, I think it was 110 or so methods that were prominently used in IREF index. We got a few biostatisticians to rank those methods. And then we used that to support our belief in whether that method was more or less reliable. So if it's a binding method, we're going to believe it more. If it's an associative method, we'll believe it less. And when the study is smaller, we believe it even less. So we ranked those methods. I think part of the brilliance and the challenge in knowledge graph backed systems is how much you're going to believe these links and how are you going to set the numbers on that. This worked really well for these studies that had their methods encoded. It also kind of works well if you trust certain resources and you don't trust other resources. But this is part of PhD work for the future as well. And this can support things like what drugs are likely to have an impact on this disease, how are X and Y likely to be connected. This was in the setting of our cancer work, but now we're doing it in the setting of some diabetes work. And it powered a personalized treatment agent that we've got a paper on that will be in the International Semantic Web Conference in October. This looked at rapidly changing staging guidelines in breast cancer, and also looked at some synthetic patient data, and then made pointed, so it's only an advisor because we're trying not to be medical doctors, but it's an advisor that says the staging is this if you use version 8 or version 7 of the ontology, points you into the treatment recommendations for guidelines. And of course, the treatment recommendations typically give some, the doc some leverage to make some decisions. And then things are annotated with the biomarkers. Oh, and actually for this one, the amount of data from version 7 to version 8 doubled. So now they consider 4 new data streams when they're staging breast cancer patients, when they determine your stage, which also dictates treatment level. So one of the reasons that I brought this up was because yesterday a lot of people said, how are you going to trust those statistical methods? I think the future is hybrid. It's crazy to ignore either the declarative things like this, methods, where you've got inference where you can understand where it came from, and it's crazy to ignore the successes of machine learning. But when some statistical method suggests something, you can go look, is there any evidence for or against this? When something like our redrug suggests this might be a good drug, can I go out to the analysis methods and see whether I get support for that? So I think, and I don't think I'm alone, I think ontologies are one of the few silver bullets around for supporting FAIR, and I'm going to add R from now on. And I didn't really show it much here, but they can support movement across different levels of abstraction. And one of my soapboxes that I get on when I teach ontologies is, please do not develop your own ontology unless you have an unbelievably good reason and you've already surveyed the literature for existing ontologies that you consider reusing. And then definitely consider myriad. Consider referencing these big, well-funded, well-maintained ontologies and importing the ones that you need. And then work in these infrastructures. So the knowledge graph can be hidden behind the scene, the ontology can be hidden behind the scene, but let them advise your decisions. And so I live for collaboration. I am truly an interdisciplinary ontologist, and I'm really excited about toxicology. So please come talk to me, because I want my ontologies to be reused and I want to make an impact on the world. And also there's a forthcoming book if you want to learn a little bit more about ontology engineering. So with that, I'll end.